Welcome to the Archives of IT. Scientists, technologists and medics talk here about how they have used computing, data and communications in medicine. Denis Noble describes how he used an early computer to construct a model of the human heart that explains the mechanism that makes it beat. But we start 8 years before that with the first mathematical models of cells. In 1952, Alan Hodgkin and Andrew Huxley described a mathematical model to explain how electrical impulses in a squid's axon or nerve fibre control its water jet propulsion system to make it move. This discovery of fundamental electrical phenomena in cells was a major breakthrough in understanding how the body works and earned Hodgkin and Huxley a Nobel Prize in 1963. The squid was good to study because its large, simple structure was easy to experiment on. However, the maths were still complex, and computers as we know them were only just being applied to science and commerce. Hodgkin and Huxley had to solve the equations painstakingly using a hand-driven calculator. Denis Noble talks about modelling the human heart. 8 years on from Hodgkin and Huxley, a young research student, Denis Noble, now Professor Emeritus at the University of Oxford, aspired to solve the related but much more complex problem of understanding how the human heartbeat is controlled. In 1960, Denis used a state-of-the-art Ferranti Mercury computer to do his calculations. Professor Noble's work opened up a whole new field of computer modelling of the body, enabled the development of new drugs, and provided insights into evolution.
I was strongly motivated to try to see whether I could do exactly what Hodgkin and Huxley had done just 8 years previously on nerve excitation. They developed the first mathematical model of a physiological process. But I went to, first of all, see whether there was a way of doing it by hand. There was. In the laboratory, there was a Brunsviga hand calculator. Most people will not know what that is, but it's a great big machine. You turn around with your hand like this, and you can do multiplications and divisions and so on. It crunches away. Oh my goodness. I calculated it would take me 6 months to do a single calculation. So I learned that University College London had access to the only big mainframe computer in the whole of London. It was situated in London University. It was called a Ferranti Mercury. And this machine was extremely valuable, extremely expensive, but very slow. Nevertheless, it was capable of doing in 2 hours what I calculated would take me 6 months to do by hand. Somehow I forced myself to learn the Mercury autocode, which is what the programming language was, and started to get some rubbish. Well, that's what happens when you first program a computer, of course. You make all kinds of silly errors. There are bugs in the program. So I got introduced to the next stage. You have to debug your program. So I spent the first few weeks just debugging the programs and eventually getting some slightly nonsense figures out, some real numbers at last, but they showed something fascinating. After each electrical pulse of this model heart, which I was building, there was the hint that it would take off again. It was trying to do another pulse. And I thought, well, this means that if I fine-tune the equations within the limits of the experimental technique that gave us the results, maybe it would take off again, and I would have a model of cardiac rhythm. And that's exactly what happened. So 6 months from getting access to the computer, I had a paper in Nature showing that it worked. So that's how I did it. Well, I tell you, for a young research student looking for a thesis, it was unbelievable. You know, I don't know what bigger problem you could have had in those days than reproducing heart rhythm, to produce a model of heart rhythm.
Each of these short videos describes a medical breakthrough made possible by information technology, in the words of those who achieved it. For more detail and extended interviews, visit our website at archivesit.org.uk. We are grateful to the support of the British Society for the History of Science for supporting this project.